So here are two examples in our book that we are going to look at. Determine the rate law expression for this reaction. Okay, so basically here's my reaction, which means in theory, I should have rate always equals your constant times the concentration of all your reactants raised to some power. And our goal is to figure out what X and Y is based on this data. So we need to find A first or B first, doesn't matter, right? Actually, A is constant on the first two and B is doubled. So this is times 2, and what happens to my rate? Nothing. My rate is unchanged. So when I double my B, nothing happens to my rate. What does that mean? What is the order with respect to B? That's going to equal 0. It's the rate's unaffected by the concentration. So now here is 2 to 1 or 2 to 1. So this is double, okay? But I need to figure out where my B stays the same. So my B stays the same here and here. So from here to here, I'm times 2. Okay, and why do I have to use these two? Because I need my B to be held constant when I figure out what A does. And my rate goes from 4 to 16. So that is times 4. So when I double my rate, or when I double my concentration, my rate quadruples. That means A is to the second order. So what is the overall reaction order? Well, let's write our new rate law. Rate equals K, A to the second, and B to the 0. So I don't put B in there at all. Okay, so my overall reaction order is 2. Okay, so now here is our next one. Write the rate law. So my rate law is going to be rate equals K, concentration of NO, and I need to figure that out, and concentration of O2, and I need to figure that out. Okay, so here my NO is doubled. 0.15 to 0.3, my concentration is doubled, and I picked that because my O stays constant here, right? So what happens to my rate? And if you put that in your calculator, what you want to do is always put the large number divided by the small number. So you kind of put it in flipped and you get it 4 times, okay? So that means that my nitrous oxide is in the second order, okay? Now, my oxygen is doubled here and here, here and here, here and here, but I need to keep my nitrous oxide constant, okay? So this is 15 and 15, that's constant, and this is 15, and that's 3.0, okay? So when I go from here to here, that's kept constant. That's great. And this is times 2. So what happens to my rate when I go from there to there? And that is times 2. So when I double my oxygen, my rate doubles. Okay, and here my nitrous oxide is kept the same. So that would be to the first order. If you double something and something doubles, it's to the first order. If you double it and it becomes quadrupled, it's the second order. So now what do I have to do to solve my K? Well, I have my formula right there, and I need to pick any one of these experiments. It doesn't matter. So let's pick this bottom experiment, number 4. That's what I'm going to put in. So I get my rate, let's just rewrite this, equals KNO2. Okay, so my rate is 0.3 0.384 molarity per second. And that's going to equal my K times my nitrous oxide, which is 0.030 squared. So that's going to be molarity squared times my oxygen, which is 0.03. Okay, so when I get all that, 0.03, that is going to equal, let's see, 0.384 molarity per second is going to equal K times 2.7 to the negative fifth molarity cubed. Why? Because two of those, molarity times molarity times molarity, molarity cubed. So I need to divide by 2.7 times 10 to the negative fifth molarity cubed divided by 2.7 times 10 to the negative fifth molarity cubed. Okay, so 2.7 times 10 to the negative fifth, divide both sides by that, and you're going to get 1.4 times 10 to the fourth molarity to the minus 2 second to the minus 1. Why? Well, I have 2 molarities on the bottom, right? I have 1 on top and 3 on the bottom. They cancel out. I have 2 on the bottom, and my second is on the bottom.